started, I just want to make sure you have access to our recording for the Monday lecture. So because of the technical issue, I have to redo a recording for my Monday lecture. So check it out and see if you have access to it, or having any problem, just let me know. And the other question is, I hope you all have access to our lecture note now. I think on Monday we'll also have some problem. So you should be able to see a blank copy of the note and a normal annotated version of the note on our Brewing Learn. And any questions on those things? No? Okay, and any other questions regarding like discussion session, administrative, syllabus, etc.? All right, and this format works? Okay, sounds good. All right, so let's get started, picking up from where we left over, which is the first part, the math review, right? So in our end of our Monday lecture, we went over derivatives, partial derivatives, and how to solve more complicated derivative questions. You'll see those in your discussion worksheet. So today is just finishing up on the math review, which is integration, right? So basically integral is now we have the differential and you want to know what these differential adds up to, right? So differential is like breaking your function into like small parts and now we're adding them back. So integration, we have two different types, right? Either you have the indefinite integral, which basically just asks you to solve for what that function used to be before you do the differential. And in this case, we're saying like y is basically a function. Well, so fx is being integrated by having the indefinite integral sign in front of it. We can also have definite integral. So basically you're just taking the integral between a range, between a to b. So that's more or less just doing a calculation and you'll actually get a number. So the difference is here, this one you get an equation as the output. And if you're doing a definite integral, the chances are you can get a more like a number out from it. Or also an expression, don't make it too. And for integral calculation, the same applies. We have a bunch of useful equations that you see in your math class. I'm not going to go over it like one by one, but effectively just know where to find these equations where you actually see these problems. And that's all I ask for. Okay, but before we move on, let's just look at one quick question together as an example problem. So the example I'm showing, well, we have like two more calculus or integration examples you can practice on yourself, and you can find the answer of these two problems on our annotated note. But let's do the problem 1.65 together. So we can read it together, right? So A, it tells you what's the differential of fx over x, and asks you to find what is fx. And B is giving you an integral or the result of an integration and ask you to find fx. So let's work on this together. So in the first part of the problem, what we can do is times dx on both ends of the equation that's provided. So what we end up having is the derivative of function fx equals to 2x to the third plus 3 exponential 5x dx. Right, so the question asks us to find what is fx. Now the answer becomes quite obvious. What we're doing is taking the integration on both ends. So doing that, we have the integral of the fx and the same integral of 2x third plus 3 e to the 5x dx. Right, so on the left-hand side, this integration just give us fx. And on the right-hand side, the equations we're using is here, this one, dxn, and also the exponential one. So I'll copy these two down just for your reference. Yeah. And you can solve that integration pretty easily. So this one ends up to be, well, 2 times x to the 4th over 4 plus 3 times e to the 5x over 5 and plus some constant c. And obviously we can simplify this to be 1 over 2. All right. So the thing that we need to pay attention to is know how to move the terms and how to use integration or taking derivative. So we can do, what the kind of operation we can do is taking integration on both ends, right? So, or move or times like dx on both ends. All right. The second part here, which is, well, if we know what this integration is, can you find out what is fx? So this one, I'm not going to actually do the calculus, but I just want to give you a hint that doing the derivative will basically undo the integration you want. So in this case, what we have is the integral of fx dx is 3 to the 8th plus c. So taking the derivative will undo the integration and get you what fx is. So try it yourself, and you'll be able to find the answer key on our annotated notes. Your textbook also have answer key to selected problems, so that's also a very nice source for study. Any questions before we move on from our math review? No? Okay, sounds good. So let's move on to more thermodynamics. So now we're moving on to talk more about thermodynamics. So in our last lecture, we went over some of the definition of terms and also math review. So today, hopefully we'll go over the most simplistic system we can think about, which are ideal gases. But before we do that, let's first equip ourselves a little bit with what is temperature. So we will give a more careful discussion of temperature later on after we discussed heat to have a thermodynamic temperature defined. But for now, let's just stay with what we call thermometer temperature. So the idea here is using the zeroth law of thermodynamics. So we all know there are like 3 fundamental laws of thermodynamics. This one is called zeroth law. It's after people discover the 3 laws of thermodynamics, they think like, okay, so this one must hold true for everything else to be true. So it comes later, but it's more fundamental. So we bring it up first. So we read it together. Let's see. We have 2 systems that are each found to be in thermal equilibrium, with a third system will be found in thermal equilibrium with each other. So in this case, this is a nice example in why you should get super familiar with terms, right? So for example, we went over definition of system. So what is a system? So the definition of the system reads the macroscopic part of the universe that we care about. So in this case, we'll just say, hey, we have 2 systems that we care about. They're just part of the universe that we care about. And if these 2 systems are in thermal equilibrium, again, we went over the definition of thermal equilibrium in our Monday lecture. So thermal equilibrium tells you adding a non-adiabatic wall will not cause any change. And if the 2 systems are in thermal equilibrium with each other, and then, if 2 systems are in equilibrium with a third system, and then they must be in equilibrium with each other. It sounds very jargon-like, but if you think about it, you have 2 cups of water, right? And you use a thermometer to measure the temperature of them. Now, if the thermometer and your first cup of water are in equilibrium with each other, we have an idea about what that temperature is. And then you use the same thermometer to measure the temperature of a different cup of water. So if your thermometer is in the equilibrium with that second cup of water, means that your first cup and the second cup have the same temperature with each other. All right. And typically, when picking a thermometer, we want to choose something that always expands when heated. So mercury is a very good one. It always expands, and it has pretty high density. It's not going to change its volume too much. And you might want to think about it, why liquid water is not a suitable reference. And we'll come back to it when we talk about the phase diagram of water. So this is just a quick introduction to thermometer temperature. Next one, in the ideal gas law, we also have number of moles to play. So in this case, we have the mole. You went over that in general chemistry. I just want to give it a more careful definition on every kind of terminology we will be using relevant to the number of moles. Now we have the Avogadro number that's defined based on the number of carbon atoms, carbon-12 atoms in 12 grams of carbon. And it is a little bit confusing. Now we're talking about atomic weight versus atomic mass, or molecular weight versus molecular mass. So these two are different kind of things. So in this lecture, whenever we talk about atomic weight or molecular weight, what we are saying are like these are the relative atomic mass or relative molecular mass. Or the other way to put it, these are the average mass of an atom or molecule to the mass of some standard. So these are unitless properties. So for example, if we ask you what is the atomic weight of carbon-12, so it's just going to be 12 without any unit. All right, so these are unitless. And the symbols are like AR or MR. Alternatively, if we refer to atomic mass and molecular mass, what we are saying are these are physical mass of an atom or a molecule. So these will have unit the same as your normal SI unit for mass, which is like gram, or you can use AMU, which is atomic mass unit. All right, a little bit jargon-like, but just bear with me. Next up, we are more often going to use the chemical amount, which is the number of mole. Right, so this is what we will be using whenever you see the abbreviation N. Or more specifically, we can define like the total mass, the big M, of a substance I equals to, well, the molecular mass of the species I is defined as the mass of that species I over the number of mole of that species I. Okay, and at the last, we have mole fraction. So mole fraction is also going to be a unitless property. So this chi I is defined as the number of mole of the substrate of interest, or substrate I, over number of mole of total number of moles available. All right. Yes?
I'm a little bit confused on atomic weight and molecular weight, on how it has no units.
So these are just relative numbers. So they're by definition saying they are the average mass with respect to some kind of standard.
Can you make the standard anything, or is the standard?
So this one we have the commonly accepted to be like, I'm pretty sure it's 1 AMU. I have to double check on that, but these are just with respect to some standards. Okay, so this part should be very straightforward. Just pay attention to details whenever looking at true and false problems in our chapter N problem. Okay, now let's get to the more exciting part, the ideal gases. yes, exciting to some extent. So ideal gases are defined as gas molecules do not interact with each other. Or the other way to put it, when we're talking about ideal gases, what we are saying is that there are zero forces between molecules or gas molecules. Right, so you can just think about them as like random dots moving in space. They do not interact with each other in any way. They don't bounce to each other. They don't occupy any space. They're just like point. And well, when talk about ideal gases, we will be talking about different kind of properties like pressure and volume. So in this case, let's talk about pressure and volume and also their unit first. So there are standard unit, which is SI unit. So for example, for pressure, the SI unit for pressure is Pascal. So Pascal is defined as like 1 Newton per meter square. So Pascal is a very small unit if you think about it. It's like 1 Newton per meter square. And as a matter of fact, when we're talking about pressure in the field of physical chemistry, we do not use Pascal as often because it's too small a unit for us to use. More often, you will experience units like torr. So that's a pressure exerted on at 0 degree by that column of Hg. Don't know why I forgot. And 1 millimeter high, and we have the gravitational constant G equals to 980. And we also use atmosphere, like ATM and bar, or for the pressure we care about. So as we can see, like we have larger numbers that we will be using. Or there are like larger pressures that we care about than 1 Pascal. And also for volume, typically you have like liter or dm cert or meter cert. So going back to ideal gas law. So when we were talking about ideal gas law, in our last lecture, we went over 2 laws, right? One is Boyle's law and Charles' law. So last lecture, I already gave you what the equations are, but let's look at what are the original plots and what exactly, how exactly do we read these plots in physical chemistry. So both Boyle's law and Charles' law are more or less experimental law. So these are physical chemists doing experiments and get the curve and then derive equations to describe what is observed in the curve. So in this case, what we find out whenever reading the scientific figure, what we have is first look at the axis, right? So on the y-axis, we have our pressure. And you can see this one is talking about pressure in atmosphere or in ATM. So that's how we read it. And in the x-axis, we have volume. So if we compare the graph we get in our Boyle's law, which is measuring the change of pressure by changing the volume while keeping the temperature and the mass at constant. All right, so you can think about someone measuring the pressure change with respect to volume change of a cylinder of gas while keeping temperature and mass at constant. An easy way to think about it, put it in a constant temperature water bath, and then you close the system so the mass of the gas will remain the same. And we observe how the pressure and volume change accordingly. So looking at the graph, what we have is it's the same shape as the graph of y equals to 1 over x. So on the right-hand side, that's just a typical graph you'll see if you have y as a function of x, which is y equals 1 over x. So what this tells us is that we have pressure equals to constant over volume. at constant temperature and mass. So in this case, K is the constant we're referring to. And the reason we have two different curves here is, as you can see, when taking the measure at different temperature, both of them give you the same kind of relationship, that pressure and volume times together equals to a constant. But that constant might be different depending on what temperature we're looking at. All right, so this is the Boyle's law. Next one, we have the Charles law. So again, this one is a experimental law, and what they did is a thermal expansion of gases. So what does it mean by thermal expansion? It's, in this case, we're saying this figure on the y-axis, that's the volume of the gas we care about. And on the x-axis, that's theta, is the thermometer temperature we were talking about. So it is a temperature, but right now let's call it thermometer temperature. Later we'll replace it with ideal gas temperature. And then later we'll give it a more careful definition to make it thermodynamic temperature. But the x-axis is temperature, all right. So now we're talking about the thermal expansion of the gases. So now it's a very straightforward linear relationship. So like volume equals to A1 plus A2 times theta. And each curve is measured at constant pressure and mass. All right, again, whenever we say a constant pressure, we're just saying this line is measured at constant pressure, P equals to 1 atm. But you can have multiple lines measured at different constant pressure. And the interesting thing of this diagram is that by taking the measurement of the thermal expansion of nitrogen gas in this situation, we find out if you do the extrapolation of these linear line, they always meet at the same point. So later on, that's our absolute zero, which is the 0K, and we will talk about it later on. Or this one is about negative 273.15 degrees Celsius. All right, so the original idea is quite straightforward. People were like, okay, so they all meet at this point. And obviously, your volume cannot be a negative number. So this point must be of some very significant importance for us. So that's how people define the ideal gas temperature, which is saying like the triple point of H2O, which is like 0 degrees Celsius, well, a little bit beyond 0.1 degrees Celsius. And that's how we define our 0K here. So one of the curious questions you might think about is, what if now imagine you went back in time to a world that you don't know what the absolute zero is, right? You don't know what that absolute zero is. What kind of experiment will you design to try to find out what that absolute zero is in that hypothetical world? Just out of curiosity. Right, so this is the kind of experiment people use to determine the absolute zero. We have more sophisticated design, but the idea is the same. All right. And I left a sample question here, which is just transferring of unit. So this is pretty straightforward. You can try it yourself and see how they match with our annotated note or your textbook answer. But before we move on to talk more about ideal gases, Do we have any questions in this part when we talk about Boyle's law and Charles' law? Yes.
Going up back to the Boyle's law,
Yes.
what does the K value represent?
So this one we will talk about it later on, but right now that's irrelevant. Just knowing it is a constant. We'll very soon talk about what is K. All right, so let's look at the actual ideal gas law. So this one is a little bit going backwards, right? We all see PV, we all know like PV equals nRT for ideal gases. So now let's just start from zero, right? Now imagine we're the physical chemist back in like 1700 or 1800, where we only know Boyle's law and Charles' law. How do we derive the ideal gas law from these two experimental observations? All right, so we'll do this together. It'll be fun. So imagine we have an initial state. And remember, when we're talking about a thermodynamic state, we have different macroscopic properties, right? So in this case, the macroscopic properties we care about, including like pressure, so we call it P1, volume, we call it V1, temperature, we can call it T1. And let's just make our life easier by setting this system to be a closed system, so the mass that we care about will always remain the same. And at the final state, I think it might be easier if I do it on the board, actually. So let's just... So we have P1, V1, T1, and we'll just keep mass as constant. And at the end, what we want to get is a final state. And in the final state, we're changing all three properties to P2, V2, T2, and we'll keep mass to be the same. And the armory we have is Boyle's law and Charles' law that I'm just going to put it up there. Now, we cannot change it all at once, right? So remember, in Boyle's law, we're saying constant temperature and constant mass. So we can use it first to have a step one. So in step one, we're keeping temperature as constant and only change P and V. So we're moving to an intermediate state. Where my pressure is changed from P1 to say PA, volume is changed from V1 to VA, my temperature remains the same, my mass remains the same, like these remain the same in my first step. And then using the Boyle's law. What does the Boyle's law tell us? We have pressure times volume equals to some constant K. So in our first process, what we have is P1 times V1 equals to PA times VA equals to some constant K. It's just using Boyle's law. We're just saying like for every process that's kept, the temperature and mass are kept constant, the product of pressure and volume always equals to a constant. And then changing from my intermediate state to my final state, we want to use our Charles law and also in step 2. in this case, we can keep, wait. Right, so in this case, we're keeping the pressure to be constant. So effectively, I can just replace this one to be P2 because it's going to be constant anyway. So we're just keeping that pressure as constant. And we have our Charles law, which is saying our volume is a linear relation. With respect to temperature. Or in this case, because it is a linear relation, what we're saying is the slope on this linear relation will be a constant value. Or the other way to put it is V2 over T2 well, equals to VA over T1. So this is the set we're looking at. Okay, with me so far? All right, and the next step, what we have is combining these two together and derive our ideal gas law. So what do we have here? So this one, this relation coming from step 1 will tell us what VA, our intermediate, is as P1 V1 divided by P2, which is this here. And then this one here, what we have is plugging this V1 into our second equation here. And we get V2 over T2 equals to P1 V1 over P2 T1. That's just plugging the number, nothing fancy. And then what do we have? Let's move the terms, like P, 2 goes with 2 and 1 goes with 1. What we have is P2 V2 divided by T2 will always equals to P1 V1 divided by T1. All right, so going back to our hypothesis, what do we have in this equation? We have constant mass. That's one of our hypotheses we use. And these two will always equal to each other to some constant. All right, so by only using the Boyle's law and the Charles law, what we have derived is even if we change all three, the pressure, volume, and temperature, from one state to a different state, this relationship will always hold true. The P1 V1 over T1 will always equals to P2 V2 over T2, equals to some constant at constant mass. So let's take a look at that constant mass part and add our final piece of the puzzle into our ideal gas law. So what do we have? We know that the equal volume of different gas at the same temperature and pressure will always contain equal amount of molecules. So that's for ideal gases only. Or the other way to put it is that your volume is going to be proportional, increase proportional, with your number of moles, which is N. So putting that number of moles into our relationship here, we get pressure times volume divided by number of moles times temperature equals to your constant. And that is our ideal gas constant, R. we have different versions of your ideal gas constant. Like typically you have like R equals to 1.987 cal per mole per Kelvin, or 8.314 joule per mole per Kelvin. So depending on what is the unit you want to use, you have different, the ideal gas constant is there. All right, so this is a quick derivation of our ideal gas constants. There are different variations of our ideal gas constant. So PV equals nRT is the most common version people use. And well, depending on if you have the molecular mass or the big M, you can rewrite it as like PV equals to nRT. Well, PV equals to nRT. But here, we're using the big M, so you can rewrite it as the mass times RT over molecular mass. And that's, again, it's one of the versions we use. Or if you have the density of your gas, which is defined as mass over volume, so you can similarly have like pressure equals to density times RT over mass, molecular mass. So you can try derive these equations and just to double check they hold true. Or the other way to define it is for ideal gas mixtures. You can say we have different types of ideal gas, we mix it together. We have the total number of moles and the number of moles of each gas, right? So we will have partial pressure and definition of the ideal gas law later on. We'll talk about it when we talk about ideal gas mixtures in our later section. Just know there are different variations of the ideal gas law, it's just like changing it slightly. One of the example questions we have is to, like, for example, find the molecular mass of an ideal gas while we tell you the density, the temperature, and the pressure. So I'll set up this problem with you, but you can do it yourself. Like, for example, we know using the equation, pressure equals to rho divided by R over T over M. Right, so in this case, there are several things we know. What we want is the molecular mass. So we can rewrite this equation as the molecular mass equals to density times RT over P. Now, the density is given. The gas constant is known. The temperature is given. And your pressure is also given. Just note, whenever you're writing the temperature, you want to change it to Kelvin. So these should be your Gen Chem type of problem, just algebra, just a little bit of algebra and plugging numbers. All right, so this is our ideal gas section. See if we have questions before we move on. All right, so ideal gas. Now we have the ideal gas law. What exactly is the ideal gas law? If you think about it, the ideal gas law is an equation of state. So what does the equation of state mean? It tells us for every specific system, there is an equation of state relating pressure, volume, temperature, and the amount of substance. Right, so the ideal gas law is one example or the most simplistic equation of state we can think about. So an equation of state is just a relationship of your macroscopic properties, pressure, volume, number of moles, and temperature. So, for example, we have different versions of the equation of state and different ways to say it. Like this one will be a volumetric equation of state, meaning we're expressing volume as a function of pressure, temperature, and number of moles. So this N1, N2 states for you can have a mixture of different kind of substances mixed together. All right, so if you think about what we have, the ideal gas law, you can write the volumetric equation of state of our ideal gas as V equals to nRT over P. All right, and these equations of state, like our ideal gas law, they are determined experimentally. We cannot derive it. They are being measured experimentally. Like in our ideal gas law, our Boyle's law and our Charles law, they are both measured experimentally. So these are experimentally derived equations that tells you about the relationship between your macroscopic properties. In this case, if we take one step further, we can see the equation of state of any pure one-phase system, assuming it is like volume equals to number of mole times another function of T and P. So in this case, we're just saying like for any pure one-phase system, or just stating like a very simple system, you can take that number of mole or N out to write it as a molar volume. So in this case, if we replace the molar equation of state, like for ideal gases, we have V equals to nRT over P. You can write the molar volume equals to RT over P. All right, so this is the definition of molar volume, and it's pretty useful because typically we don't care about the size of the system. We're just talking about the equation of state without changing the number of moles. So that's the ideal gas law, but there are different kinds of equation of state, right? So ideal gas is only one of our system that we cared about. We can also have, for example, Van der Waals equation of state. Now, if you think about ideal gases, right, so the hypothesis we make in ideal gases are the gas molecules do not interact with each other in any way, which is obviously wrong, because if you have like gas molecules bumping into each other, they will have repulsive forces, they cannot occupy the same space, and also when you get like somewhat close, they will have attractive forces. So we have different kind of equation of state to try to describe the more realistic picture. Right, so the Van der Waals equation is one of it. We have like pressure plus AN square over V square and times volume minus N times B equals to nRT. So in this case, there are different meanings here. In the first part, what we are saying is gas molecules attracts each other. At certain distances. And on the right-hand side, this NB tells you the gas molecules now are treated as solid balls. Like they have volumes, they cannot occupy the same space instead of the volumeless points that we were referring to in the ideal gas. All right, so following up our van der Waals gas, right? They're just different kinds of equation of state. Let's see one of the example questions. Now, using our van der Waals equation, which we just provided, can you replace the volume and number of moles with our molar volume, right? So remember, our molar volume is defined Vm. So this abbreviation M tells you that's a molar volume equals to volume divided by number of moles. And next up, if you're using bars, cubic centimeter, and moles, and also kelvins as unit for P, V, N, and T, so can you derive what is the unit for A and B in the van der Waals equation? So again, we'll do this together on the board. So the first part, we're just using volume or molar volume equals to volume equals divided by N. So we're replacing whatever in the van der Waals equation, volume and number of moles, with the molar volume. So the first part is we have pressure that doesn't have number of moles or volume. And in this case, A stays the same, and N squared over V squared becomes 1 over Vm squared times. So V divided by N. So we're dividing, well, let's do this this way. V minus NV equals to nRT. And we're dividing both ends with an N, with a number of more. So it ends up having, the first part is okay, we'll leave it out. And this one becomes V over N. So that's our Vm minus B. And on the right-hand side becomes RT. Right, just dividing both ends with the number of moles. And then becomes quite straightforward. The second part asks us about the unit. So one lead rule that you feel is common sense, but just remind yourself, is we can only do plus and minus of the term when their dimension is the same. All right, so it's like you can't do mass minus volume. That's not a defined, physically defined term. So if we do plus and minus of two physical terms in our equation, they must have the same unit. Right, that's pretty straightforward to understand. And that gives us the answer to the question, like what is the unit of A and B? So in this case, your B will have the same unit as your molar volume, right? So in this question, in molar volume, we're using, well, cubic centimeter for our volume. We're using number of moles. We're using moles for our number of moles. So our B will have the same unit, which is cubic cert over mole. All right, so they must have the same unit. The same applies on the left, on this side. The pressure have the unit of bar. Right, so we have A divided by Vm squared. So this one will also have the unit of bar. So your unit of A will be your bar times mole squared divided by Cm6. Make sense? Okay, I'm running out of time, but this is a quick introduction to the equation of state. And in our next lecture, we will pick up where we left over. which now we're talking about the general rules of the equation of state. Let's not thinking about ideal gases. We're just going to think about for a equation describing relationship of molar volume, Vm, pressure, and temperature. What are the partial derivatives describing their relationships? And what kind of experimental measurement should we make in order to identify what the equation of state is? So we'll save that for our next lecture. And if you're interested, you can read them ahead of time. And again, we're using partial derivatives, so you will see us using those partial derivatives rules in our next lecture. So if you haven't done so, review them a little bit.